As you know, there are several hip stems available in the market. We call it hip stems because these are conventional hip arthroplasty or hip replacement, not the resurfacing one, not surface replacements. So basically, there is a varied, design available in the market, and different hip stems or different hip implants have different types of influence on the aseptic loosening. So aseptic loosening of femoral stems or hip stems is influenced by the following mechanical factors related to the design of the implant. Okay, so you now have a basic idea that the design of the implant, okay, has influence on the outcome of the reconstructive surgery. And this outcome of the reconstructive surgery is actually dependent on mechanical factors. Okay. Now, the stem geometry as a whole, the implant material, the length of the porous coating, as you can see that there is porous coating only if I look here, you can see the porous coating here. Okay. Partial porous coating here as well. Partial porous, not, one type of coating here, maybe another type of coating here. Coating here near the neck and more on the proximal side. So there are huge type of variants of this design of the hip stem. So, and these designs are mostly based on clinical perception, suggestions from clinicians, combined with some scientists, but a study to determine the optimal combination of these factors towards an improved hip implant was necessary. Okay, so we set out to investigate the 3D shape optimization of hip implants. Of course, we started with a generic design of, say, an uncemented prosthesis, for example. But, considering the failure mechanisms and the detailed stresses that cause failure or that induce failure, design was not, based on such considerations. Now, as you can see, this is quite an important slide. And if you look on this animation down here, and of course, in combination with generic design, which is called Trilok stem. This is still in use, Trilok, Johnson & Johnson hip stem. So let us first concentrate on existing generic design of Trilok hip stem. Okay. Now we identify basically 4 key sections, say A, B, B, C, C, and D, D. Okay. And you can see that the shape of these sections are varying considerably from AA to DD. Okay. Now this actually varies from ellipse to super ellipse. And if it varies, these are the variation of the cross section, then obviously it will translate into a 3D implant structure, which would look like that. So with variation in the 4 key sections, you can end up with different types of shapes of the trilock hip stand. Now, if you look in these 4 key sections, we can actually parameterize these sections, and this parameterization, you can see that as I told you, the curves can vary from ellipse to super ellipse according to the power 2, 3, 4, 5. Okay, so as you increase the power, the curve actually changes its shape from ellipse to super ellipse. Okay, so we can express x and y if we consider the cross section of at AA, BB, BCC, DD. We can express x and y, the basic geometry, as a function of the parameter p, and this parameter p can vary from 2 to 5. Okay, so we are actually dealing with 18 design parameters, right? So you can see A1, A2, A3, A4, A5, A6, and then P1, P2, P3, P4, all this, and V1, V2, V3, V4. So 18 design parameters we need to deal with. We need to find out the most optimum, shapes, 3D shapes that would give me minimum failure. Okay. Now, earlier studies have actually, they attempted to investigate, but they did not do it, in a holistic manner as we have taken up the study as an optimization study. So they actually, in 2007, Ruben tried these shapes, 6 shapes, to find out the most optimum within these shapes. But we are parameterizing the geometry so that we end up in a far greater number of design variables, design shapes, and then finally select the most optimal design of the prosthesis. Did you get my point? Hello? Could you follow what I said? You can. I've put it on. Students? Hello?
Yes, sir.
Yeah. So is this slide clear to you?
Yes, sir.
What is our objective? And of course the motivation and the background. Okay. So I move on with the next slide. Now, as I told you that we have discussed about this earlier, but we have not discussed the mathematical formulation of the interface debonding yet, which we will do very shortly. But we have basically 2 major objective functions. Okay, but this we have discussed in general as failure mechanisms. One is stress shielding, as we have discussed. So we are concerned about the amount of bone resorption. Okay, bone apposition is a favorable phenomenon. So if the bone density increases in and around the prosthesis, it is always a favorable situation. But if there is bone resorption, reduction in bone density, then obviously the foundation of the fixation is basically disturbed. Okay. So we would like to see minimum bone resorption, right? That is one of, to minimize on the bone resorption. So a mathematical function was defined where the resorbed bone mass fraction could be estimated. Okay. So this will be calculated in each iteration and then assessed continuously. The other objective function, interface stresses. Based on interface stresses, the normal and shear stresses at the boundary of, say, implant and bone. A Hoffman failure index can be calculated. Okay. Now, a Hoffman failure index, I will discuss this separately. The Hoffman failure index actually incorporates not only the interface stresses, but also the local bone strength. Okay, so we actually evaluate whether or not an interface will fail based on, say, a local state of stress defined by the normal and shear stresses versus the local strength, which is always the case when we assess failure in any material. Okay, so it is a combined formulation, Hoffman's failure index. We'll do that separately, but it actually it helps us to assess whether or not at any point that there would be interface debonding or interface failure due to high stresses as compared to the local strength. Now, why do I say local strength? As you know, the bone density is varying from one point to the other. Okay, and when the implant is inserted, the implant itself doesn't fail. Which is the weaker material between the two, implant and bone? The bone is obviously the weaker material. Did you follow? Hello? I put it on, students.
Yes, sir.
Yeah. So within an implant bone configuration, at the interface, the implant is always a stronger material and bone is the weaker material, if you consider its strength. Now this bone density, the bone density is varying from one point to the other, influencing the strength of the bone, right? So if it is a higher bone density, obviously that typically that location, that bone, say bony element in that location would offer you higher strength, right? But if it is a lower strength, if it is a lower density, it will offer lower strength, right? But the implant material is homogeneous and the implant material doesn't change strength from one point to the other. So obviously the bone is the weaker of the two, and the changes in bone density would influence its local strength, and thereby it will influence failure at different points on the interface where it is coming in contact with the implant. Okay, this is a very important consideration while we assess failure of the implant. So these are the two objective functions And in many cases, we will find that these two are contradictory in nature. So if you increase a dimension of a prosthesis, it may actually lower the chances of interface failure, but at the same time, it will go on increasing the chances of more bone resorption. Okay, so these may be a conflicting parameters in the whole design procedure. Okay, therefore, the need of a compromise design, a trade-off between different requirements becomes essential, and thereby we actually apply a proper optimization scheme, okay, using genetic algorithm. Perhaps you are all aware of the genetic algorithm scheme. Are you aware of genetic algorithm scheme? Soft computing?
Yes, sir.
Yeah, the GA-based technique, which can actually handle this type of problems quite efficiently. So we had undertaken that in consultation with Professor Pratihar. You people know him in mechanical engineering. So he is an expert in the development of the genetic algorithm. So we had jointly come up with this work, come up with a numerical framework or numerical optimization technique to handle 3D shape optimization. Okay, and we had applied it on this hip prosthesis, right? Now, obviously, optimization problem will have objective functions, the primary things. So minimize objective 1, minimize objective 2, F1 and F2. Subject to certain constraints. Okay. So what are these parametric constraints? There are parametric constraints. So A2 minus A1, A1, A2, I think so these are A1, A2. So there are dimensional constraints. These cannot be 0. Okay. So the dimensional constraints are mentioned here. Okay. Some minimum value it needs to have for the dimensions. Subject to, these are the conditions. Now we started this optimization procedure considering only one material. So we are not optimizing on the implant material. We are optimizing on the dimension, 3-dimensional shape optimization only. So we keep the material, titanium alloy, which is basically the material of the hip prosthesis, constant. Okay. So we start with the generic design, as I told you, the Tri-Lock hip stem here. But from Tri-Lock hip stem, we progress into different variants as suggested by the optimization protocol. So it was important to automate the shape optimization procedure, and thereby we developed a numerical framework which can handle actually 2,500 implant shapes. Right? It's not joke. More than 2,500 implant shapes were analyzed, and it was all automated. Okay, you look at the whole scheme. We start with the CT scan. We keep the CT scan image constant of particular patients, so CT image processing. So from the CT image processing, you can actually do virtual implantation using rhinoceros. So this was virtually implanted. Then automated volume meshing. Then we apply the loads, do the static analysis. Then we get hold of the stress analysis. We calculate all the failure, the values that would actually decide whether or not it will fail. So we satisfy objective 1, the stress shielding, amount of bone resorbed, and then the interface stresses. Everything is calculated for a particular design. And then we feed it to the NSGA2, the genetic algorithm scheme, to evaluate whether or not this design is acceptable. Okay. If it is not acceptable, then a new design parameters evolve. So we take the next set of values and we get a new implant model. Okay. This new implant model again is virtually implanted. This whole process goes on until we actually come up with a set of optimal designs. Okay? So you can imagine that this is a heavy computational scheme, and we keep on running the cycle until we get off some trade-off designs. Okay? So this whole scheme was published in the ASME, Transactions of the ASME, as you know, very famous American Society of Mechanical Engineers, Journal of Biomechanical Engineering, okay, 2015. So what we get as results is a lot of design space. You can see the points, but there is an optimization direction which is important to us. On one side, we have the objective 1, resorbed proximal bone mass. So the proximal side, the resorption is high. So the resorbed proximal bone mass on one side, and the global interface failure function F2, Hoffman's failure criteria using so forth. These are the two conflicting parameters we are trying to handle, and we are trying to minimize on both. And then we get this design space from which you can see there is an optimal direction of this, data points. And from this, we actually can derive the Pareto optimal font from this scatter plot. So it is somewhat like that. It's coming somewhat like that. Let me just, where's the laser pointer? Oops, oh sorry. So it is coming somewhat like that. So we are focusing on this area because that is basically the optimization direction. You can see very clearly how this whole cluster of points from the scatter is trying to converge around this region. And this is the Pareto optimal font, where we can identify optimal stem geometry 1, optimal stem geometry 2, and optimal stem geometry 3, which looks like this. 1, 2, 3. Okay? And you can see, more zoomed in also with the corresponding sections, key sections, A, B, C, D, how this is changing. Okay, but one thing to note here is that if you concentrate on the portion A to B, okay, the distal part of the implant. You can see for all the designs, the optimal design stem geometry 1, 2, and 3. These are almost very, very similar. Okay, there is hardly any change between AA1, AA2, AA3. Also for BB1, BB2, and BB3. Therefore, one important conclusion came up is that this long portion, the distal part from AA to BB, doesn't actually affect the failure mechanisms to a great extent. Therefore, there may be some other functions required where we can use long stem designs, but this mathematical or scientific calculations actually triggered the justification behind short stem designs of the hip implant. Okay, so we can find the justification through this analysis that there is actually no need of AA to BB. That means we don't need this long stem. This distal part of the stem is not contributing too much towards either failure or, say, durability of the prosthesis. Now let us compare from where we started. Okay, we have found some trade-off optimal designs. There are 3 optimal designs. But let us compare with the configuration from where we started. The generic design, the Trilok stem. So you can see here that this is the immediate postoperative condition of the bone density distribution. Now for the Trilok hip stem, on the proximal side, we have very high bone resorption, indicated by minus 55% bone resorption. This is the medial side, this is the lateral side. So lateral side we have minus 55% bone resorption, minus 67% bone resorption, proximal medial side of the reconstructed femur. Okay, minus 42% as we go down towards the diaphysis of the femur. This is on the lateral side, and minus 36%. Again, bone resorption on the medial side. Now, this whole thing, see the distribution for the first design, OSG1. 55%, it has reduced to minus 18%. From 67%, minus 28%. Minus 42% or 42% bone resorption to 4% bone resorption. From 36 is 10%. Okay. So you can cross-check that this optimal stem geometry 1 is actually resulting in much favorable bone density distribution after attainment of equilibrium in bone remodeling. If we consider OSG2 as well as OSG3, you see the values, percentage of bone resorbed for different cases. And this obviously is far less than what we had seen in case of the Trilok hip stem. Okay. You can visit these slides later on because I'll share these slides anyway, so you can have a closer look at it. But OSG1, OSG2, and OSG3, all these 3 designs are resulting in far less effect of stress shielding, and thereby you know, the bad effects of bone remodeling, or adverse effect of bone remodeling, is reduced to a great extent, thereby, of course, increasing the durability and success of the implantation procedure. So we have come up with a novel patient-specific multi-objective shape optimization scheme for cementless, and this scheme can be used for different purposes. Okay, for a cemented implant, we can actually also look into the cement stresses, the thickness of the cement. So we can go on adding different variables that influence failure of the implant. So the optimal implants, the optimal implant designs yield favorable proximal load transfer and reduce chances of interface failure. Adaptive bone remodeling was also minimized for the optimal designs. Okay, so the genetic algorithm scheme is an effective shape optimization tool, and the proposed method can serve as a major step towards customized implant design. Okay, so if there is a need for customization of the implant, we can act. This is a major step towards that by implementing this method on statistical femur model. So let us not talk about statistical femur model, which is basically a representative femur model, and that accounts for the variation in osteological parameters. So we are now going patient specific. So when we say customized implant, it means actually it is patient specific. So, boys and girls, so you have seen the power of this biomechanical analysis, right? Is it clear to you overall?
Yes, sir. Yes, sir. Yes, sir.
Now I'll finish up with within 5 minutes another very eminent study in our lab. Just listen to it. Okay, we will discuss about again tissue engineering, bone regeneration as a separate topic altogether. But just to give you a feel that how these biomechanical analysis work, I would give you a short presentation on the work of Dr. Kaushik Mukherjee. Now, Kaushik Mukherjee was my PhD student, the last PhD student. Another one, Basil, is maturing. Kaushik did very well in his career later on. He was a Marie Curie fellow. He was working with Imperial College London, and he was given this award, Marie Curie Award. And then he has joined IIT Delhi as an assistant professor in mechanical engineering, and he has started biomechanics research in IIT Delhi in the department. So just let me give you a very brief idea about his work, which was initiated here. So you can see this, we had prepared this presentation quite a few years ago. So his tenure still doesn't appear. So say since May 2012, he graduated in 2017. So he was a joint MTech PhD student. So he did MTech and continued his work for PhD. Now this is on micro scale simulation of bone ingrowth. Okay, so as you all know, this is an uncemented prosthesis. You can see uncemented hip stem, which contains an implant with a porous coating, and it directly attaches to bone. Okay, so it is a case of biological fixation. So the bone ingrowth into the pores of the porous coating actually ensures the biological fixation. So the amount of bone ingrowth in the porous coating would dictate the degree of osseointegration. Osseo means bone, and osseointegration means it is integration with the foreign material, or that is the implant. So the degree of the fixation of the implant with bone is highly dependent on the amount of bone ingrowth in the porous coating. Okay, so there was hardly any study which would give us the amount, the spatial distribution or quantitative amount of bone ingrowth, okay, or distribution, spatial distribution of bone ingrowth around, say, any implant. So we had taken, for his case, a pelvic bone acetabular implant. This was later applied on hip stem as well, but by base. So you can see the background. Cementless implants rely on biological fixation with bone, and bone ingrowth is known to follow the principle of fracture healing. Okay, so we will discuss these things later on as a separate topic. So over the last 2 decades, mechanoregulatory algorithms have been developed to quantitatively assess tissue differentiation. So we also developed a mechanoregulatory algorithm along with a computational framework to quantitatively assess tissue differentiation. Okay, so the motivation lies here, that it was necessary to gain an insight into the predictions of periprosthetic. Periprosthetic, I hope you know the term. So periphery of the prosthesis, bone ingrowth by 2 commonly used mechanoregulatory tissue differentiation algorithms. So one was the phenomenological algorithm, another was a more detailed cell-specific, cell phenotype-specific algorithm. So we took up an acetabular prosthesis with, a beaded implant, as you can see. So we had a multi-scale modeling approach. So we developed a microscale FE model representing implant bone interface, and then the objective was to quantitatively determine the tissue differentiation. Okay, so the study focuses on acetabular component, and it takes into account the variation of regional bone material across the acetabulum, and it also takes into account the very important variable, which is the micromotion between implant and bone. So implant bone related displacements. So these two actually influence the bone ingrowth to a great extent, and we had actually about I think it was 11 models that separately we analyzed, but that represented basically variation across the acetabulum. Now, what is this? Let us not go into too much detail because we will be dealing with this separately. So we have mechanoregulatory tissue differentiation algorithm. There are 2 types. One is phenomenological, another is cell phenotype. Here in the phenomenological type modeling, it is basically diffusion-based model. So it is a shortcut method. But in cell phenotype, we have more detailed modeling of the process. So cell migration, proliferation, differentiation, and cell death are modeled separately, and which is not taken care of in the phenomenological model. And here, as you can see, the cell differentiation is governed by a mechanoregulatory principle, where here we have extracellular matrix formation and tissue degradation are considered in the model. So this cell phenotype specific modeling approach is much more detailed as compared to the phenomenological model, which is diffusion based. So once it is diffusion based, all these cell migration, proliferation, differentiation, and cell death are modeled together in this case. Now, mechanical factors that govern bone ingrowth is, of course, the mechanical environment existing at the interface. Okay, so obviously you can understand that the surface texture design will influence the mechanical environment. The local property of bone, of course, there is no local property of implant property, material property doesn't change from one point to the other, but the bone material property changes from one point to other. It's heterogeneous. So, but the combination will give you a different mechanical environment from one point to the other. Boundary conditions. So, implant bone relative displacements are the boundary conditions, and these boundary conditions will influence the mechanical environment to a great extent, and thereby periprosthetic bone ingrowth. Now, what are the mechanoregulatory principles? The mechanoregulatory principle is based on certain threshold values, okay? Certain threshold values of strain, octahedral shear strain, and hydrostatic pressure, a combination of both. So, there are some certain threshold values below or above which will actually give you some fibrous tissue. Of course, a different range for cartilage formation and the different ranges for immature bone and mature bone. So based on this mechanoregulatory principle, different threshold values, threshold ranges, we can get different types of tissue being differentiated. And keep in mind that this is an evolutionary, time-dependent mechanism. And of course, tissue differentiation is a continuous process until it reaches equilibrium state. Now, as you can see, that this is the submodel of the hemipelvis being implanted, already implanted with acetabular cup. Of course, we apply the submodeling technique to analyze it, to get realistic values of stress and strain across the whole reconstructive structure. But we are actually interested here at the interface. So we take a small element here and try to zoom it up, and you can see we have the implant with the bead, very clearly the implant bead. Oops. So this is the implant body, but within the body integrated are the beads, okay? And you have the bone on the top, okay? So this is the interface, implant bone interface. But between bone and the implant, you have this interbead spacing, and the granulation tissue is filled at this interbead, within this interbead spacing, okay? So this is a macro scale model on the left, but on the right we have a micro scale model. But we will be connecting the two, giving rise to a multi-scale analysis. Okay. So features of the micro scale model and the applied boundary condition. Dimensions, total number of elements, nodes. The top surface is mapped from the acetabulum, so that is bone. The bottom surface mapped from the implant, and the lateral surface, this and on the back has periodic boundary conditions. So it's similar. Now, as I told you, there are 13, sorry, I told you 11, there are 13 regions. You can see the acetabulum being divided into 13 regions, just to take care of variation of bone material property at different locations. There are and variation of implant bone relative displacement at these 13 locations. So there were 13 models that were being monitored. So all bone, quantitative spatial distribution of bone ingrowth in 13 models representing the whole implant bone interface. Now you can, within this, based on the results, we can actually color code few things. We have actually identified 4 regions, key regions, which are representative based on the amount of bone ingrowth. So 12 to 25% bone ingrowth is happened in these regions. Okay, 4, 10, 7, 6, 7, 13. Black is 45 to 55%, quite high. Purple is 60 to 70% bone ingrowth. Okay, and blue is 75 to 90% bone ingrowth. So we actually select one of each color code and try to present the results. So we select 5, 7, 8, and 9, okay, of each color code. So you can see here region 5, region 7, region 8, and region 9. So 5 is here, and 7, 8, 9 is more towards the periphery, whereas 5 is more towards the center part of the acetabulum. But you can see very clearly 3 types of tissue. Fibrous tissue here is blue. You can see here fibrous tissue formation. Cartilage formation, the green one, and immature bone formation. Okay. Now, if you look into the results more deeply, the average Young's modulus of the newly formed tissue layer, it started with granulation tissue, but later transformed into different kinds of tissue. So when it is getting transformed into different tissues, we can see that the average Young's modulus of the region 5, 7, 8, and 9 is increasing. And obviously, the strain in these regions, intermediate spacings, the newly formed tissue layer is decreasing, which means that the stiffness of the newly formed tissue layer is on the rise, is increasing. That means there is more bone formation already in the newly formed tissue layer. Now, the average Young's modulus of the newly formed tissue layer was observed to increase with time in all the 13 regions. We just, as representation, we have just represented 5, 7, 8, and 9. But in all the 13 regions, this trend was visible. The strains in the newly also decreased, strains also decreased, and similar pattern was observed by Isaksun, paper by Isaksun earlier in 2006. Now, as I told you, this is a simulation, so we need to actually validate. And validation was not possible as we could not do direct experimentation or clinical feedback studies. We had to rely on other studies being performed. So overall, the FE predicted bone ingrowth that was predicted by our study was about 46%, averaged over 13 region, single acetabular component. Whereas the clinical and histological, or the clinical studies, mainly histological and radiographic studies, indicated about the same value, around 46%, in 76 different acetabular components. So this is earlier study, titanium acetabular shell. Variation was 20 to 83%, but average was 46%. They had used 76 different acetabular components. And this is a quite old paper. They did some histological studies, and the porous coated acetabular ingrowth, 33% of bone ingrowth was observed in 9 different acetabular components. Okay. So with this comparison, we had the confidence of accepting the whole modeling procedure and moving on with different types of predictions. But the basic question was not answered very clearly because we had a phenomenological method of predicting tissue differentiation. We had a cell phenotype, very complex cellular mechanisms being implemented in the tissue differentiation algorithm. Okay. Now, the best thing was to compare on the same model. What was the output? You can see the percentage of bone ingrowth after reaching equilibrium. This is the final configuration. For zone 5, 7, 8, and 9, these final bone ingrowth predictions were quite comparable. You can see similar trends. Quantities between 60 to 70% zone 5, almost equal in zone 7, little minor differences in zone 8, and almost similar in zone 9. Okay. So what was the problem? Phenomenological model is a much simpler way of tissue differentiation algorithm, of implementing the tissue differentiation algorithm, whereas cell phenotype was a far more complex, with all the cellular mechanism being modeled exclusively or explicitly. So if we try to monitor the evolutionary process of both the methods, we can see a lateral shift. The white is the phenomenological model, and the yellow is the, or orange is the cell phenotype model. And we see that both are comparable almost, okay? But still there is a lateral shift which is noticeable. And this lateral shift is basically due to inclusion of different cellular mechanisms and the coefficients of different cellular mechanisms that influence the process. Okay? The delay the process is basically a delay, as you can see. On the x-axis we have the iteration, days. But the final configuration, when it reaches equilibrium, I can refer back to the slide, it is giving almost similar results. Okay, so the overall tissue differentiation predictions of phenomenological and cell phenotypes algorithms were found to be similar. The cell phenotype specific algorithm of prime importance when cellular interaction with implant surface is required to be studied. So of course, there is a benefit of a much more detailed algorithm implementing the cell-specific algorithm. But the phenomenological algorithm, being computationally far less expensive, is a suitable alternative to the cell phenotype algorithm in order to gain an insight over periprosthetic tissue differentiation process. So, thank you for listening. I think we are almost there. So we can discuss about this tomorrow because it's already time, isn't it? Hello?
Yes, sir.
Yes, sir.
Sir.
But I think it is quite fascinating for you to see the complete, now the biomechanical analysis, modeling and analysis lecture is complete up to this. But individually, I will take up tissue differentiation, this whole thing as the last lecture, the last topic. Okay, we will discuss more in detail. But I think this is quite fascinating for you to notice. We have published all these papers. Everything is published. And you can see or realize the power of biomechanical analysis, modeling and analysis. So I'll see you tomorrow at 11. Okay? Hello?
Okay, sir.
Yeah. We can discuss about it. In the meantime, I will upload this presentation. And tomorrow we can discuss.